Hello guys, in the last class we had spoken about aromaticity, aromatic, non-aromatic, anti-aromatic compounds and resonance energy, and now we have already covered all the electronic effects which are important to understand the basic mechanism of the reactions. So now today we will understand how these factors affect the acidic strength of the molecule and how do we compare and judge the acidic strength of different compounds, right? So let's start with the acidic strength. First of all, we should know what exactly acidic strength means, or what is the parameter to judge a compound whether it is acidic or not. So there are multiple different definitions which we follow to decide or to tell whether a compound is acidic or not acidic, or it is acidic or it is basic, or what kind of character it possesses. So for acidic character, we have three different definitions. One is given by Arrhenius. According to it, any compound which is H plus donor is known as acid. Any compound which can give H plus when dissolved in water in H2O. I must mention in H2O. When dissolved in water, when it releases H plus ion, then the compound is called as acidic. This definition we have already learned in grade 10th also. Another concept or another definition for acidic strength was given by another scientist, Bronsted-Lowry. And what was the definition here? Any proton donors are called as acids. Anything which can give H plus without water or with water, anything which can release H plus ions are called as Bronsted-Lowry acids. So difference between Arrhenius and Bronsted-Lowry is Arrhenius was very specific to solubility in water, whereas here any compound which is capable of giving H plus ion will be called as acid. Third type of acids, or third type of definition for acid, is Lewis acids. Anything which can accept the pair of electron are called as Lewis acids. Anything which can accept the electron pairs are called as acid. So for example, I have written HCl here. When dissolved in water, it is broke down into H3O plus and Cl minus. So this HCl has given H plus in water, so that way it is following the Arrhenius concept also, and the Bronsted-Lowry also, because it is proton donor, and it has given H plus ion in water also, so it is following both. Let's say AlCl3 if I have, and I take Cl minus. Cl minus is this. So here aluminium has an empty orbital, and this chlorine can give its pair of electron to this aluminium to form a coordinate bond. AlCl4 minus can be formed. Because of the empty orbital present in Al, it can accept the pair of electron, and that acceptance of pair of electron makes it Lewis acid. So here in AlCl3, aluminium is acting as a Lewis acid. So Lewis acid is anything which can accept the pair of electrons. Okay, so these are the different definitions of acids. Now there are different scales to measure the acidic strength. So first scale is Ka value. Ka value, we have already spoken about Ka value in physical chemistry. You must have heard of this term earlier also. So what is Ka value? How do we calculate it? If I have a acid in equilibrium, Ha will break down into H plus and A minus. So equilibrium constant of that acid is Ka. And how do we write it? The concentration of products divided by concentration of reactant. Okay, so basically concentration of H plus A minus divided by concentration of Ha gives you the equilibrium constant Ka, and this Ka tells you the acidic strength. Okay, so if Ka is more, if Ka is higher, or value of Ka is higher, the acidic strength will be higher. If the value of Ka is lesser, the acidic strength will be lesser. So we have understood what is exactly Ka value. Ka is nothing else but the equilibrium constant of acid when it dissociates. It gives you H plus and A minus. So concentration of H plus A minus divided by the concentration of acid is called as Ka. More the value of Ka is, more will be the acidic character in that molecule. Now the another thing which we use for determining the acidic strength is pKa value, which is nothing else but minus log of Ka. So basically here you can also say that pKa is inversely proportional to the value of Ka. So that means if Ka value increases, the value of pKa decreases, and hence the acidic strength decreases. Or you can say if pKa decreases, then the acidic strength increases. So whatever the behavior of Ka is, pKa will be opposite of it, and hence the acidic strength will be opposite of it. If pKa value is increasing, acidic strength will decrease. If pKa value is decreasing, acidic strength will increase. Now what I have done here is I have listed down some molecules or some compounds with the pKa values, so that we can relate, we can understand The values are not important over here, as in like you don't have to mug up the values, but it is good to know that which is more acidic, which is less acidic. And in table, or you do when you do the comparative study of the organic compounds with the inorganic compounds or different organic compounds, you should know the basic differences and most importantly the exceptions in the acidic strength. Okay, so I have taken the first acid, that is HSBF6. This is also called as super acid. It is the most acidic acid. This is an inorganic acid. The value of pKa is -12. -12. Okay, then comes your H2SO4 with the value of -10, HI -9, HCl -7. So all of these are inorganic acids, which are pretty strong acids. Now comes one organic acid, which is among the organic acids is a very strong acid, that is PHSO3H, which has very equal value when you compare it with the inorganic acids, and that is PHSO3H, basically benzene sulfonic acid, SO3H. This is the molecule, and this has the value of -6.5 pKa. So acidic strength is pretty high, right? Now as you can see, the pKa value is lesser here, so lesser means more acidic strength. Least pKa value means most acidic strength. Now when you talk about H3O+, H3O+ is capable of giving you H+, will have a pKa value of -1.8. When you talk about organic acids, their acidic strength comes lesser than these acids, the inorganic acids. And you see, you have formic acid over here. The value of formic acid is +3.7. So way higher than the values of the inorganic acids. If the pK value is higher, the acidic strength is going to be very low. So HCOOH, and you can see here the benzoic acid is given. So benzoic acid with the value of 4.2. So even lesser acidic than HCOH. This is exception, so mind it, formic acid is more acidic as compared to your benzoic acid, and this is exception. Why? Because your aromatic acids are more acidic as compared to aliphatic acids. So all straight chain acids will have relatively lesser acidic strength as compared to the aromatic acid, but exception is your formic acid. Formic acid has higher acidic strength as compared to your benzoic acid. So this is an important exception. And you get questions on this. Then comes your CH3COH, which is lesser acidic than your benzoic acid. Then you look at CH2ClCOH. Now here what we have done is we have seen that ethanoic acid is lesser than the benzoic acid. Here what we have done, we have already understood the behavior of inductive effect and how does it affect the acidic strength. So basically we had CH3COH, its acidic strength was very low. Now what we have done, we have replaced the hydrogen over here with one chlorine. So basically one electron withdrawing group is present, which will increase the acidic strength of this molecule drastically. And when you see the acidic strength is increased, you can easily compare it with the ethanoic acid. Ethanoic acid has value of pK is 4.7, whereas here the pK value is 2.86. Lesser the pK value, more will be the acidic strength. It has become now even more acidic than your benzoic acid and even more acidic than your formic acid. So basically addition of one electron withdrawing group to your molecule is making it very, very acidic. And this is something which we have already learned in inductive effect, but we can see the value change over here, which will help us in relating it in much better way. So now next few more compounds. Next we have is H2CO3. H2CO3 is what? It is H2O plus CO2. This is also called as carbonic acid. The value of carbonic acid is 6.4, very high value for pKa. So hence very, very, very less acidic. Okay. Similarly, let's compare CH3CHO. It's aldehyde, very high value for pKa, almost no acidic character. Water is 15.7. Again, it's neutral. Look at this, CH3CH2OH, ethanol. So 16 value, even lesser acidic than water. It's very less acidic. It's lesser acidic than water. And this is almost equivalent to this molecule. What is this molecule? This molecule is dimethyl cyclopendiene sort of structure. And it is very less acidic. Why this is very less acidic? Because it doesn't have hydrogen to lose from this point. So if it would be just cyclopendiene, ene sort of structure, then it would have lost hydrogen from here and would have gained the aromaticity. So basically from this carbon, if hydrogen would have gone, there would have been a negative charge and it would have become cyclopentadienyl, and this molecule would have become aromatic. But this cannot become aromatic by losing hydrogen, and hence it is not acidic. So the value is 16, pK value is 16, its acidic character is almost negligible. Look at this molecule, we have more and more electron donating groups present around OH. More electron donating groups present decreases the acidic strength of the molecule, and hence this molecule is further has higher value for pK, and its the acidic character is decreasing. Look at this, more number of methyl groups are attaching on this alcohol, more electron donating groups are adding, the acidic strength is decreasing, and the value has become 18. So this is just an implementation of what all we have learnt earlier. So let's talk about phenol. So when you're talking about phenol, phenol preferably wants to become phenoxide ion. What is the reason behind it? See, we have phenol and phenoxide ion. When we are comparing which is more, why phenol wants to become phenoxide ion? Because it will lose H plus, will become this. And when you're talking about the phenoxide ion, this is much more resonance stabilized as compared to phenol. So both of these things, phenol as well as phenoxide ion, both are giving us 5 non-equivalent resonating structures. 5 non-equivalent resonating structure, but let me just draw one out of 5. So when you're talking about phenoxide ion, this is let me draw. So this is like this. I have O minus, and this is the ring. So this O minus will give its electron density here. This will go over here. So this will form something like this, O, and then you have a negative charge here, double bond here, and so on. So this negative charge will keep dispersing in the ring. So how and when we're talking about phenol, let me draw the phenol resonating structure also. So when the phenol will form the resonating structure, it will form like this. So basically negative charge is dispersing in the ring, but there is a positive charge on oxygen. So what is the difference between phenol and phenoxide ion resonating structures when both are forming 5 equivalent resonating structures? Why phenoxide ion is much more stable than phenol? Look at phenol, there is a charge separation over here. Oxygen is gaining a positive charge, whereas the negative charge is getting dispersed inside. And we had spoken about the stability of the molecule through the resonance. When we are talking about the resonating structures, which resonating structures are much more stable? The ones where the charge separation is lesser, or you can say the positive charge is not on the electronegative atom. Those kind of structures are more stable. Here the negative charge which oxygen was carrying getting dispersed in the ring altogether, and basically the negative charge strength is decreasing and getting distributed throughout. Whereas here, when the resonating structures are forming, oxygen is getting a positive charge which is opposite to the behavior of oxygen. Oxygen is electronegative atom, it must get the negative charge, but it is getting positive charge over here. Though octet is not disturbed, so it can carry positive charge, but definitely it is not a true nature of oxygen. And hence when you compare the resonating structure of phenoxide ion resonating structure of phenol, phenol's resonating structure is lesser stable than the phenoxide resonating structure, because the oxygen is carrying a positive charge and negative charge is on the atom or element which is lesser electronegative than oxygen, that is carbon. So negative charge is being carried by the carbons and getting distributed in the ring, whereas more electronegative atom is carrying a positive charge. That makes these resonating structures lesser stable as compared to the phenoxide resonating structures. And that is why we say your phenol wants to lose hydrogen and want to become phenoxide ion, because that will give it better stability. And that is how your phenol is acidic, will like to lose the hydrogen and will become phenoxide ion, because phenoxide ion on resonance becomes much more stable as compared to the normal phenol. We have phenol and we have put 3 electron withdrawing groups, NO2, 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 and you see the acidic strength, you see the pK value, it has dropped drastically. It is very less value, and hence acidity is, or acidic character is very high. Exactly same way benzoic acid is acidic, but addition of electron withdrawing group will make it further more acidic, and the value will come down to 0.65 pKa. That means acidic strength is very high. NH3, it's basic. Look at its pK value, 37. CH triple bond CH, though we call alkynes are acidic in nature because their terminal hydrogen, or you can say terminal alkynes, have acidic hydrogen, they lose H plus ion. But look at the pK value, it's 25. That means very, 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 very less acidic. Look at the alkyne and look at the alkenes, the value is 40, almost no acidic. CH3 almost, it's no acidic. I mean, pK value is way too high. Okay, so these are the comparisons over here. You have to remember that HCOOH is much more acidic than your aromatic acid, that is benzoic acid. In general, aromatic acids are more stronger acids as compared to the aliphatic ones. Why? Because benzene ring is electron withdrawing. So electron withdrawing, and that makes the acids much more stronger. But your HCOOH is better acid than your benzoic acid. So this is how aromatic acids, I have written it over here, aromatic acids are stronger than the aliphatic acids, but formic acid is an exception. This exception you have to remember for the acidic strength. You don't have to remember the data, you don't have to remember the pK value, but at least you should be able to relate it logically using the resonance factor or inductive effect or hyperconjugation, what all different electronic effects you have learned till now, what all can be implemented, you have to implement, and then you have to compare the acidic strength. So basically any electron withdrawing thing will increase the acidic strength, or any electron donating group will decrease the acidic strength. This we have already discussed earlier, but again we are just talking about it so that we can get an overall picture for acidic strength of the molecules. Now let's look at some examples and try to implement whatever we have learned. So we have RSO3H and RCOH. We have to compare their Ka values. That means we have to just compare the acidic strength, and acidic strength of your sulfonic acid is better than your carboxylic acid. Why is it so? Because you look at this molecule, look at these structures. This is your carboxylic acid, this is your sulfonic acid. When it will lose H plus, it will form RSO3O minus, and this will form RCOO minus. When you draw the resonating structures of it, it will form three equivalent resonating structures, whereas this molecule, that is carboxylate ion, that will form two equivalent resonating structures. More the equivalent resonating structures are, I mean, generally how do we compare the stability of the molecule? We see the equivalent resonating structures, whichever the molecule is giving equivalent resonating structure is much more stable than the non-equivalent one. When both are giving equivalent resonating structures, then we'll see the count. So here this is giving you more equal RS, and more equal RS means more stability. More stability means your conjugate base, what is forming after losing H plus, is much more stable. If the conjugate base is stable, that means it is a better acid. Okay, so your SO3H, RSO3H is much better acid than your RCOOH. So acidic strength depends upon multiple things. We have, as I mentioned, we have to relate it with all the electronic effects. What we have learned, apart from that, acidic strength also depends upon what is the conjugate base forming after the H plus is lost. When H plus is broken, then whatever the conjugate base is forming, how stable it is, that will also decide what is the acidic strength of your molecule. So if your A minus or your conjugate base is stable, your acid strength is more. If your conjugate base is weaker, your acid strength is lesser. So we will compare the conjugate base stability. How do we compare the conjugate base stability? There are some points which we have to list down, and we have to understand to see whether a particular conjugate base, what is forming after losing H plus, is stable or not. So strong acid forms stable anion. Stable anion means nothing else but the stable conjugate base. Stable conjugate base. So if you have stable anion means when you have acid, that is HA, it will break down as H plus and A minus. So this A minus thing, H plus and A minus. So this A minus thing is your anion or conjugate base, whatever you want to call it. So more stable your conjugate base or anion is, better acid will be your molecule. Now let's talk about on which all factors the stability of anion depends. First of all is electronegativity. If electronegativity of the atom where the negative charge is, the electronegativity increases, the stability of anion increases. So basically, if your atom which is carrying the negative charge is more stronger electronegative element, that means the stability of anion is better. But this rule is followed only when you're going from left to right. So basically in periodic table, if we are talking about, we are comparing two species, and those two species have the two atoms which are in the horizontal relationship in the periodic table, or you can say are in the same period, then only this rule sets or this rule fits. Otherwise, if they are going from top to down in the same group, then the rule differs. So when you're comparing in the same period, when the elements are present and they have the negative charge in them, and you're comparing those species together, basically you have two different molecules to compare. One has O minus, let's suppose, and another has N minus. So both of these atoms belong to the same period when you go from left to right, and whichever atom has the more electronegativity will make a better stable anion. So basically this rule fits only in the period, not in the group. So What exactly this means? Let's say I have the four compounds present, CH4, NH3, H2 and HF, and I want to form the conjugate base of them. So conjugate base of them will be CH3 minus, NH2 minus, OH minus and F minus. Now I have to compare which one is better acid. So I will see the stability of the conjugate base. As I mentioned, more the electronegativity of the atom is, more stable will be your anion. So here your F minus has the maximum electronegativity, hence it is the most stable anion. Then comes your OH minus, then comes your NH2 minus, and then comes your CH3 minus. So basically we are comparing F minus with O minus, N minus and C minus. Right? So F minus being more electronegative, most electronegative is most stable anion. Then your O minus has a better electronegativity. Then this is better. You can say a better conjugate base, a better stable conjugate base than NH2 minus and then CH3 minus. So if somebody will ask me what is the acidic strength, how would you compare the acidic strength? So in that case, HF is gonna be most acidic acid, then H2, then NH3, and then CH4. So that's how we will relate the acidic strength when the negative charge is carried by the atoms which are present in the same period in the periodic table. So we will go by electronegativity. What happens when the atoms are present in the same group in the periodic table? In that case, size will matter. So basically, size of negative charge carrying element. More the size is, more stable the anion will be. So basically, bigger your atom would be when you're going from top to down in the group. More bigger your atom will be, more easily it will be able to carry the negative charge. So basically, it will be able to disperse the negative charge properly on itself and will be able to handle that negative charge. Smaller the atom would be, more concentrated the negative charge would be, and it will be difficult. Basically, the existing electrons in that atom will repel that negative charge, and that's why the molecule or that anion will become unstable. So for example, if I compare fluorine with iodine, so when you're going from fluorine to iodine, the atom size is increasing. Now if I say that I am comparing F minus, Cl minus, Br minus and I minus, in that case what exactly is going to happen? Negative charge, the charge strength is same. So F is carrying one negative charge and I is also carrying one negative charge, but the size of iodine is bigger, and hence that negative charge can disperse throughout on the iodine atom. Whereas when you talk about the fluorine has the negative charge and it has its own lone pairs also, and everything is concentrated in a very small area, so the chances of repulsion is much more as compared to the stability. So when you talk about F minus will face the repulsions internally, because it has its own lone pairs also, and it has negative charge also. That negative charge is again due to the electrons. So those electrons, those extra electrons and its own existing electrons will repel each other and will bring the instability in the molecule. So here we will not talk about the electronegativity, here we'll talk about the size. So bigger the sizes, easily the negative charge can be handled by the atom, and hence better will be the acidic strength. Okay, so if I compare, as I mentioned, HF, HCl, HBr and HI, I will have four conjugate bases: F minus, Cl minus, Br minus and I minus. I minus has a bigger size. Bigger size means it will be able to carry the negative charge very easily, because it will be able to disperse it throughout, and repulsions will be lesser. Repulsions between that negative charge and the lone pairs which are present with the iodine will be relatively lesser. Whereas when you go to the smaller sizes, the negative charge or the extra electrons and their own electrons, or the atom's own electrons, will be much more closer, and more closer the electrons will be, more will be the repulsion. So I minus will be more stable with the negative charge, whereas F minus will be least stable with the negative charge, and hence when you compare the acidic strength, HI is gonna be the most acidic acid, whereas and then the acidic strength decreases. So HI is most acidic, then HBr, then HCl, and then HF. So here size matters, whereas when you go from left to right in a period, the electronegativity matters. Now the third factor which can affect the acidic strength of your molecule is presence of electron withdrawing group. As I have discussed this already, that electron withdrawing group, if it is present in the molecule, it increases the acidic strength of the compound. So that electron withdrawing group can be in either way. It can be through the mesomeric effect, it can be through inductive effect, it can be through minus hyperconjugation. So any of such effects are working will increase the acidic strength of the molecule. So here I have taken some list of examples where we are seeing the application of all these electronic effects, and we are deciding the compound's acidic strength. So here we have CH3COH, CH2Cl-COH, CHCl2COH and CCl3COH. So here what we have taken is ethanoic acid and its derivatives, and at every carbon we are increasing the chlorine. So increasing chlorine means what is happening? minus I effect is increasing by chlorine. So basically, more the number of Cls we are adding, more electron withdrawing groups are getting added. More electron withdrawing groups are getting added, the molecule will become more acidic. So here in this molecule, there are 3 electron withdrawing groups, that is 3 chlorines present on the carbon, which is neighbor of COH. So 3 electron withdrawing groups will increase the acidic strength drastically. Basically, will pull the electron density towards itself, and the oxygen hydrogen bond will also get a strain, and the cleavage of oxygen hydrogen bond will be much more easier. Now, when you talk about CHCl2 COH, again 2 electron withdrawing groups. So acidic strength will be lesser than CCl3 COH, but at least will be better than others. So CHCl2, presence of 2 electron withdrawing groups will increase the acidic strength. Then comes this one, and then comes this one. So CH3COH will have least acidic strength because no electron withdrawing group is present. So that's how we have arranged them according to the increasing Ka order or increasing acidic strength. Exactly same way we have the next compound set, HCOH, CH3COH, and CH3CH2COOH. Now COOH is the acidic group over here. Here if you look at it, CH3COH is there, so CH3, which is present over here, is an electron donating group, not a withdrawing group. It's a donating group. It has a plus I effect, so basically acidic strength will decrease. Now when you look at CH3CH2, 2 donating groups with COH, so basically acidic strength of COH will further decrease. Right? So this one will be the least acidic, then comes this one, and then comes this one. So this one will be most acidic, and this one will be least acidic. Why? Because I have electron donating groups. Electron donating groups decreases the acidic strength of the molecule. Next, PHCOH is greater than CH3COH. Why? pH means benzene is electron withdrawing, whereas CH3 is electron donating. So in both the cases, COH is the acidic group. The acidic group strength will increase if electron withdrawing group is present, and will decrease when electron donating group is present. That's why benzoic acid is more acidic. Here we have already spoken about the exception. HCOOH is more acidic than your benzoic acid. So this you have to remember. This is very, very important. Now again, let's arrange these in the acidic strength order. Here no electron donating group, no electron withdrawing group. Here 1 electron donating group, that is CH3, and here we have Cl as an electron withdrawing group present along with the CH2COH. So how will be the acidic strength? This will be most acidic because electron withdrawing group is present. Then comes this, neither electron withdrawing nor electron donating, and hence and the next is the second one, because it has electron donating group, the acidic strength will be least. Okay, so in this case, where the fifth compound is, we have RCOH and and phenol. We have to compare the acidic strength. We have RCOO minus. RCOO minus gives you 2 equivalent resonating structures, whereas when you talk about the phenoxide ion, it gives us 5 resonating structures which are non-equivalent. So even though the number of equivalent resonating structures are lesser than the non-equivalent one, that gives more stability. Hence my aliphatic carboxylic acid is gonna be much more acidic than your phenol. Okay, so this is about the presence of electron withdrawing group or electron donating group and their effects on the different compounds with respect to the acidic strength. Let's see a few more examples on the application of this. So let's compare in this compound the acidic strength. This is my primary carbon, this is my secondary carbon, this is my tertiary carbon, which is most electron donating. Tertiary carbons or tertiary carbon attachments are more electron donating because a lot of carbons are present, a lot of crowding is present, and they all are electron donating groups. So when you're talking about this OH, the acidic strength will decrease of an alcohol when the more electron donating groups are present. So here distance matters. So if you see, the distance of carbon with OH is decreasing. Here the carbons are attached in the linear manner and the carbons are going far from each other, whereas here the carbons are very close to the OH. Electron donating groups closer to the OH means more the number of electron donating groups closer to the OH will decrease the acidic strength. So this is gonna be least acidic, then this one, and then this one, right? Or you can compare it with the stability of the anion also. So see here, if all these species lose H plus ions, they will form O minus, O minus, and O minus. So here electron donation, direct electron donation is from this carbon with the distance electron donation is decreasing. Negative charge will increase more because of the electron donation of the carbon. Here the negative charge will be further more because electron donation will be from here, from here, from here. Distance is relatively lesser. The carbons and the oxygen minus distance is relatively lesser. Here in this case again, this carbon will donate its density, this carbon will donate, and this carbon will donate. So here least electron density is getting donated, whereas the maximum electron density is getting donated in this case. So unstability of O minus is increasing in the third case, right? So basically you can compare it with either ways. More electron donating groups or more closer electron donating groups are there, lesser will be the acidic strength. Farther the donating groups will be, or distance with the electron donating groups is increasing, the acidic strength will be increasing. So basically, farther the electron donating groups are, lesser will be the electron donation and lesser impact will be on the acidic strength. So first primary is more acidic, then secondary, and then tertiary. Now we have further few examples over here. I have written some compounds and then we have to arrange them in the acidic strength order. We have CH3OH, H2O, CH3CH2OH, NH3CH triple bond CH, and CH3 single bond CH3. So now what I'll do is I'll write their conjugate bases and then we will see the stability of those conjugate bases. So I have CH3O minus as a conjugate base, OH minus, CH3CH2O minus, NH2 minus, CH3C minus, and CH3CH2 minus. So if you remember, I was explaining you in the table with the pKa values that when you talk about basically this alkanes are least acidic, hence this will be anyways the least acidic one. Then comes your ammonia. Ammonia is basic in the nature. Its Ka value or pK value, its pK value is very high. Then it has some acidic character over here due to the terminal hydrogen. So alkane is least acidic. Then comes your NH2, and then comes your alkyne. Now let's compare these three compounds. So if you remember, when I was giving you the pKa table, at that time I had given you the value of the pKa value for CH3OH and H2O. Though the value for the pKa value for CH3OH and H2O is nearly same. What exactly is the value? Value for CH3OH is 15.5 pKa value. And when you talk about the water's value is 15.7. Very slight difference, but the value is higher for water. pKa value is higher for water. That means it is less acidic as compared to CH3OH. So CH3OH is more acidic than H2O, even though it has one electron donating group present over here. So this is also an exception, similar to I have spoken about the exception before, that is HCOOH is more acidic than PHCOOH. Exactly same way we have one more exception, that is your methanol is more acidic than water. And any other alcohol is lesser acidic than your water, but your methanol is more acidic than your water, and it's very slight difference, and that we have got through the pKa value. pKa value is higher for water, lesser for CH3OH. Lesser the pK value, higher is the acidity. So here, even though the funda says that CH3 is donating group and hence acidic strength of CH3O minus or CH3OH should be lesser than water, but still pKa value says something else, and hence the first one is most acidic, then your OH minus, and CH3CH2O minus, two electron donating groups are present, making this anion much more unstable, hence the acidic strength of this CH3CH2OH is lesser. See, whenever electron donating groups are present, they increase the negative density around the atom. And if the electron density is increasing around the negative atom, basically it is becoming unstable. So CH3, CH2O minus has two donating groups, CH3 and CH2. Both are donating to O minus, increasing the negative density and hence unstabilizing the anion. If the anion is not stable, your acidic strength is lesser. So OH minus has neither donating nor accepting group, or neither donating or nor withdrawing group, so it is anyways a normal group. CH3O minus has a donating group, but according to the pKa value, the things come a little different. Your CH3OH is slightly acidic than water, hence we will go by exactly pKa value. Even though when we look at the CH3OH, it looks a little different. It looks like water should be more acidic than CH3OH, but we'll go by pKa value, and CH3OH is more acidic than water. So one is most acidic, then second, then third, then comes your fifth. Fifth is your alkyne, then comes your NH3, that is amine, which is basic, and the least acidic is your alkane. So that's how you arrange, and that's how you compare the acidic strength. Okay, so now let's look at this question. In this question, I have given four OH groups. Four OH groups, one here, one here, one here, and one here. So four OH groups, all the four oxygens have the four acidic hydrogens. So what will I draw? I'll draw the, I'll write the conjugate base of it. I'll remove the hydrogens because I want to check the acidity, and we will see which is giving you the better stable base, better stable conjugate base. So now look at it. If I remove hydrogen from A, what will happen? It will form an alkoxide ion. This will get into the conjugation with this double bond. So here is the negative charge. This will conjugate here, and this will do the resonance like this. So this is the resonance which will happen with this oxygen, right? So this oxygen will do resonance like this. Now look at B. B will do resonance from here to here, right? Look at the position C. If O minus has been removed from here, what kind of alkoxide this is? This is a tertiary alkoxide. And if I look at D, this is a primary alkoxide. So now we have to see which is the most stable. So basically B and A both are giving you the resonance stable alkoxides. So basically giving you resonance stabilized anion. Now when you look at A and B, in B the resonance is more than A. In B, when B is removing its hydrogen from the B position, when the hydrogen is getting removed, it is extended conjugation till here, from OH to this carbon, then this carbon, then this carbon, and then oxygen. So this has more number of resonating structures as compared to this OH. That is why B is more resonance stabilized than A. Then comes D and then comes C. We have already seen that the resonance, we have to see if the resonance is there, then that will stabilize maximum. Then comes your inductive effect and all other effects. So basically due to the resonance, B and A are very stable, but B is more stable than A because B is making more resonating structures. Now let's come to next question. In next question what we have two positions. One is this A, another is this B. And now we have to tell which position is more acidic. So we have to find out Ka here. So if I'll remove hydrogen from position A, then what will happen? One negative charge will appear over here and H plus will come out. This negative charge will be in conjugation with this double bond and with this oxygen. So basically resonance will happen from here till here, right? Whereas if I'll remove hydrogen from B, let me just draw it. So if I have a negative charge over here, this is not in conjugation with anything. So position A, if you get a carbon ion there, position A is much more stabilized due to resonance than B, and that is why Ka is more than Ka for A is more than B. Now let's look at the next question. I have COH and COH. Now again we have to remove hydrogen and we have to check the acidity of this acid. If one hydrogen will get removed, the H plus will come out and it will form COO minus, right? So COO minus, and there is a COH group. So this CO minus group is getting stabilized by minus I effect of COH. So COH is electron withdrawing and stabilizing this negative charge, right? This is for Ka1 when one hydrogen has been removed. When the second acidic hydrogen will be removed, it will become CO minus at one place as well as CO minus at another place. Now if you look at these anions, this negative charge or this conjugate base, rather than being stable, it is becoming unstable due to the plus I of this CO minus. So if you look at this COO minus thing, this CO minus is unstabilizing this CO minus and this CO minus is unstabilizing this CO minus due to its plus I effect. This is electron donating. These are the electron donating groups rather than electron withdrawing. So now when you look at the acidic strength or look at this conjugate base is very unstable base. Whereas the first base what we had created, the conjugate base, that was a stable base. So if I compare the acidity or if I compare the Ka value of first one is better than Ka value of second one. Or you can also say that when you are talking about the dicarboxylic acid, when it shows the acidity by removing only one hydrogen, then it is more acidic. When it removes both the hydrogen, then it is less acidic. So its acidic strength will change or its acidic strength will decrease if it will remove more H plus ions. So with the release of single hydrogen, it is better acidic. With the release of two hydrogen, it is less acidic. So basically, even though it has two acidic hydrogens, it will preferably remove only one acidic hydrogen only, because removing two acidic hydrogens is making your system unstable. Now let's compare the acidic strength of these two acids. So we have two acids. One is, so in both of these acids, if you look at it, these are dicarboxylic acid with a double bond here. So COH, C double bond, COH. So this is COOH, CH double bond, CHCOH. Because this is an alkene, this can exist in cis and trans both forms. So cis form of it is called as maleic acid. Trans form of it is called as fumaric acid. Now we have to see whether the acidic strength varies if we change it from cis to trans. Now look at the cis form. If I'll remove H plus from it, as I mentioned in dicarboxylic acids, we prefer removing only one H plus because that is better acid than removing two hydrogens. After removing two hydrogens, the conjugate base what you get is less stable than the removal of one H plus. Okay, so only one H plus we will be removing. As soon as we'll remove one H plus, you'll get a negative charge over here. So this is your CO minus, and this CO minus, look at it, I have just drawn it in a little different way. So COH, I have written C double bond OH over here, and this oxygen and hydrogen, this negatively charged oxygen and this hydrogen of the other COH will try to form the hydrogen bonding. So there will be a hydrogen bonding here due to the presence of hydrogen bond, which oxygen and hydrogen will form over here. This will become much stable ion. Understand this thing, wherever the hydrogen bonding comes into the picture, it increases the stability of the molecule. So here oxygen and hydrogen will form the hydrogen bonding. Over that, it is 6-membered cyclic chain, 1, 2, 3, 4, 5 and 6. 6-membered cyclic ring it is forming by the hydrogen bonding. So 6-membered cyclic ring, when it forms with the hydrogen bonding, it is very, very, very stable. Okay, so it is making this anion very stable. Now let's look at the next transform of it. If I'll remove the hydrogen from one COH, it will get CO minus, and here there is no relation at all over here. This is not going to form any kind of hydrogen bonding with this because the direction is different and it cannot form the hydrogen bonding like this. It's very far off. So if you talk about the stability of first molecule which has formed by cis and the another conjugate base which is formed by trans, cis conjugate base is much more stable than the trans conjugate base. That is when one H plus has been removed. Now let's look at the second removal of hydrogen. If second removal of hydrogen takes place, the Ka2, what it will be, there will be 2 CO minus will get generated, and these are two negative ions very close to each other, so there will be high repulsion. So in that case, your Ka1 and has much higher value as compared to Ka2. So in this case, Ka1 is much greater than Ka2. In the next case, look at it, if I remove the another hydrogen, it will form CO minus and CO minus here. Basically, we wanted to compare the acidic strength of Ka1 of cis and Ka1 of trans. We got to know that in case of cis, Ka1 is much better due to the stable bonding, stable hydrogen bonding, hence Ka1 value will be greater over here. Whereas if I compare the Ka2 value of cis is very less, and because there is a lot of repulsion over here, let me just write it properly. There is a lot of repulsion in case of cis, whereas if I talk about trans, in case of trans there is no repulsion, they are very far off, so Ka2 value will be much better. So if you compare the trans Ka2 value and the cis Ka2 value is way lesser because it's very unstable as compared to Ka2. So comparison here, Ka1 value of cis will be better and Ka2 value of trans will be better. So this is how we compare the acidic strength of the molecules and how we will compare the Ka values. All these logics you have to understand, implement, and then find out the acidic strength of the molecules. And that too, when you are finding Ka value, you have to check which Ka value they are expecting, the removal of first hydrogen, removal of second hydrogen, all these things you have to keep in mind, and accordingly you have to solve the question. Okay, so here I have shown you some examples. In next video I will be talking about a very special effect that is called as Ortho Effect, which works on the specific type of compounds and which affects the acidic strength of the molecule drastically. So we will be talking about Ortho Effect, we will be talking about steric inhibition of protonation, steric inhibition of resonance, and we will see their implementations in acidity and basicity of the molecule.